Have you ever heard of the possibility of glass flow? Today, I invite you not to look through the glass, but to look at the glass. Do you know if glasses flow? I'm Lancelotti, a PhD student in Material Science Engineering. In this video, I will tell you about this. Let's get started! So, what do you think? Does glass flow? I mean, will a glass flow over a plate driven by gravity after a certain amount of time at room temperature? You have probably seen people making glassware through the process known as glass blowing. It consists of heating raw glass material to a high temperature so that it becomes malleable, then inflating the molten glass using a blowpipe to form a bubble, which can be molded into containers or sculptures. It's important to understand that although this material becomes glass after it's cooled, during the glass blowing process, the material being molded is still a supercooled liquid. This liquid has a very high viscosity. Viscosity is a measure of the liquid's resistance to flow. For example, consider two bottles containing two different liquids. One with low viscosity, like water, which is 0.01 poise, and one with higher viscosity, like honey, which can be 500 poise. If we tip these two bottles over at the same time, after about 10 seconds, the water will have flown and spread out, whereas the honey will flow out and spread much more slowly. During the glass blowing process, the material is at temperature of approximately 1000 Kelvin, with viscosity of 10 to the power of 7 poise, which is still enough for the material to flow slowly under its own weight. This viscosity is 10 million poise, which is a billion times greater than that of water. The liquid-glass transition occurs at a higher viscosity level, 10 to the power of 13 poise, and at a temperature of approximately 800 Kelvin. Below this temperature, the glass becomes rigid. Estimates of glass viscosity at room temperature are higher than 10 to the power of 20 or 40 poise. Now that you have learned something about viscosity, I have a question for you. Can glass flow at these very high viscosity levels? There is an urban legend about the apparent flow of stained glass in medieval cathedral windows. Interestingly, people have sometimes asked me about this. They say that the stained glass in old cathedral windows in Europe is thicker at the bottom than at the top. Researchers around the world have discussed this topic. The first scientific article in this area was published more than 2 decades ago. This subject is still of general interest, as the myth still persists in our society today. Studies have contributed to this subject, but in general, they have all reached the same conclusion. Cathedral glass flow is only a myth. The variation in thickness cannot be assigned to glass flow, since the flow is estimated to be 1 nanometer in a billion years, where this 1 nanometer is 7,000 times smaller than the thickness of one hair. The stained glass in cathedral windows are not one whole piece of glass, but rather they consist of several pieces of cut glass. Most glass pieces have a non-uniform thickness. This is related to the manufacturing methods used in medieval times. These pieces were probably made by blowing the liquid into a cylinder and then splitting and flattening the glass manually or through the chrome process. These pieces are not uniform in thickness. Not only can we find pieces that are thicker at the bottom, but pieces that are thicker at the top can also be found. Thanks a ton for watching. See you!